Okay, so this video is try to give a very short introduction for the Fourier series, and basically the textbook is follow the Kruzak and Afkin. Okay, so the first definition is that f of x equals to f of x if f of x plus p equals to f of x for some p larger than 0, then we would just say that f is a periodic function. F is a periodic function with period p. Okay, so this is the definition, and it's common sense that so example is like 1 with period 0, sine is cosine x, and the tangent of x, then there's also the cosine n of x, sine n of x. Okay, and that is with period 2 pi, and this with period pi, divide 2 pi divided by n. Okay. Okay, so definition. So the triangle metric series, it basically is a form of this. So there are different notations. Some people will use a naught divided by 2, but I would like to use but in the textbook we use a 0. Okay, so if somebody give you f of x, then I define a Fourier coefficient, a not just 1 over 2 pi the integral of f. So f is period 2 pi. So f is a function of period 2 pi, and the bn is just 1 over pi, and pi f of x cosine nx dx, and pi f of x sine nx dx. Okay, so this is the definition. Okay, and okay, and so basically that's it. Okay, so we can show some try to show some examples. But I think showing examples is not useful in the video. So I will try to prove the theorem before showing the example. Okay, so the theorem is that so at least the lemma we need is the orthogonality. So orthogonality basically we contains 3 orthogonalities. One is this, and the second is if you have 2 cosine, then basically this is 0 if m is not is center n, and the sine if m is not equal to n. Okay, and for this one is for any n and m, basically for any n and m are integer. Okay, so the proof is very simple. So I think I only prove this one. Okay, so the proof, basically if you have these two, then you can just use write as this: cosine m plus mx plus a half cosine m minus mx. Okay, so this is definitely 0, and then this is non-zero because you take any cosine kx to 0 must be integral from pi to pi must be 0 unless m is equal to n. So when m is equal to n, this is just 1. So you will get answer pi. Okay, and the same as the others. Okay, so okay, so that's it. Okay, so the key point is that what we want to show is the f of x and the Fourier series of f of x. So the relationship of between it. So key point is the relationship. Okay. Okay. So the theorem basically say that if if f is continuous at point x naught, then series converge at x naught. Else f of the series at x naught converges to the limit, the right limit, and the left limit divided by 2. So this is the theorem. So basically, what we are saying is that if x naught f continues at x naught, then the Fourier series converge to the same points. And if x naught your f of x does not converge, then the Fourier series will converge to the average of the middle points, the middle points. Okay, and this theorem is not easy to prove, but the convergence is easy to prove. The convergence of the Fourier series is easy to prove. I think we don't have to prove it here. But we may assume that. But we may need to assume that this f at least can do the double derivative. Then you can prove that it must converge. Okay, so let me see. Okay, so let me give a short proof. Okay, so what we need to prove is the Fourier coefficient must converge. So suppose I only take an and this is the coefficient, right? So we can use the integration by parts. So we get this, and then we do the derivative prime of x on this function. And what we have is so this turns 0 because sin n pi minus n pi is 0. So an is minus this one. And we can still do it at least twice, so we'll get this. So if you do it, we'll get this. Okay. Plus, so this is 0, and then we use the integration by part again. So what we have got is this. And then this is still 0. Okay, so what we have got is this. Okay, so this is the coefficient of an. Okay. Then suppose we assume. Let me change it. Suppose we assume double prime of x is bounded. Okay, then what we will have is the an will bounded by n squared pi squared, and bounded by this, right? This is m times 1, so m dx pi inverse pi. So we have so 2m divided by n squared pi. 2m divided by n squared pi. Okay, so we have this 2m n squared pi. Pi, right? But I can just write it down as 2m divided by n squared. Okay, so the same reason as bn will less than this. Okay, so your total for a series basically is a naught plus an cosine x plus an bn sin x. If you take this is so-called like Weierstrass M test. So the first one a naught. So a naught is bounded because if I assume that f is continuous or bounded function on the integral, then it must be bounded. So this a9 is a9 is a finite number plus the 2n divided by n squared. Sorry. And also Bn. So this is finite, right? Because we all know that 1 over n squared is finite. Moreover, you know that this is pi squared divided by 6. So this is finite. This is finite. So which tell you that the f is finite. So and f absolutely is less than infinity, which tell you that this f converges. Okay. Okay, so this is the proof. Okay, so basically what we have developed is that although if I didn't prove here, what we have developed is that the Fourier series can have some converge property, can converge to some point of the original period function f, and then we derive the actually we didn't derive, right? But we somehow like say that this coefficient. I somehow tell you a result that this this series already reflects some properties of the function f. Although I didn't tell you how to show this function. And from next time we just change the period p and try to see whether there are some interesting things that we can do. That's it.